All right, so now let's take a look at possible outcomes and see how do we deal with an impact situation that we have objects colliding uh, in each case, for each case, right? So let's put it under possible outcome. I'll go with, let's just start with the first one, the most straightforward one, that is basically when we have two objects A and B, and there's an impact and they collide and they stick together. Right? You can think about two sticky material, like maybe two pieces of mud, I guess. If there is an impact between these two, just they stick together and they move together. Right? If that's the case, that's that we are gonna basically put that in this category as an example of this outcome. So let me write it this way: if A and B uh, adheres, let's say, and remain adhere and remain together after they collide, we actually call that it is a perfectly plastic impact. It is a perfectly plastic impact. Right? And by that I mean, let me bring the figure I believe I have. Hopefully that's the right figure. There you go. It's from your textbook, so I think it makes it a little easier to actually imagine what's going on. So A and B, they're moving, they collide at some point here. There's an impact there, and then they stick together. They stay together and they just move together with velocity v. Right? In that case, if you use the total linear momentum that we talked about, like the conservation of linear momentum, right? MAVA prime plus MBVB prime is equal to MAVA plus MBVB. In that case, the velocity after impact, VA prime and VB prime are the same because these two become one object and they move together. Right? The masses add up. So MA and MB, you just add them up, becomes one mass. Like this becomes the mass. And it moves with the velocity that is the same. They're going to have the same velocity. All right. So from that, you can actually find this velocity, the velocity after impact. Remember, we said the whole story is that you want to study dynamics, you want to know what is the relationship between velocity before and after the impact. So in this case, if A and B they stick together and they move together, then from that relationship, you can find the velocity after impact. Right? You know MAVA plus MBVB. I have to be more careful. These are all vectors. Remember, we said when we're dealing with momentum methods, we treat velocity as a vector. Right? It's not energy method anymore. So we have to be mindful of the direction of these velocities. Right? We'll see in examples that positive, negative, if it's in two-dimensional space or three-dimensional space, you have to remember there are components along different axes. So these are vectors. I have to be probably a little more cautious and put the vector signs there. From there, I will get MA plus MB. Right? So they stick together, they form one mass, one object which has a mass of MA plus MB, and one velocity. And this V, right, just to emphasize, I'll write here, this V is the velocity of the center of the mass of the object formed by A and B after the impact. All right. So there's an impact. They stick together. They remain together. They form one object, and that object has the velocity v. See if I can box this equation. And I have to remember, this is also a vector, momentum method. This is one possible outcome of an impact of two objects. The second one will be the opposite of the, or if this is not the case, right? If A and B do not stick together, do not stay together, do not adhere together, and they get separated, right? That would be the second possible outcome. So outcome 2, or possible outcome 2, one of these happen if A and B don't adhere, then there are two, then we might have, I'll put it this way. So outcome 1, pretty straightforward. Outcome 2, if they don't stick together. We're going to also create two cases for this outcome. I will say case 1 for outcome 2 is when there is direct central impact, meaning that A and B travel along the same straight line. So they come together on a straight line, there's an impact, they get separated under the straight line. They go on their way. Or maybe there is an impact and they go both in the same way. Or maybe they both are going the same way. This is going faster, the other one, so this goes this way, this one comes faster, there's an impact. They both are traveling along the same line, there's an impact, and then they continue their way. Right? Because of impact, some of the energy of this is going to be transferred to this one, and they still continue on a straight line, same straight line. So this is case 1. So possible outcome 2, case 1 would be the direct central impact. That's what we're going to talk about today. Then we'll cover the second case, where we have a situation that this impact is not on, these objects are not on the same straight line, right? They can come, again, that example of a pool table, a ball is hitting the wall or a ball is hitting the other one. Usually there is an angle, right? It comes with an angle, they hit, and then they get separated. That's what the second case is. Now, let's just stick to the first case. Right? Case 1. There we go. If I can make this work, there you go. So this, we'll say case 1 is the case where I should have to put the title here. It has a name, as I said. It's direct central impact. And that happens, as I said, centers of A and B, if you think about these two objects as like rigid bodies, they have a center of mass, right? These centers travel along the same straight line. So centers of A, I can probably do a better job here. Centers of A and B travel along travel along the same straight line. All right. So they are moving. I actually have the figure from textbook again here. That's a pretty good, I think, descriptive situation. So we have object A, I have object B, two rigid bodies, two particles. A is moving to the right, B is also moving to the right. A is going faster than B, so they both are moving along, traveling along the same straight line. A is going faster than B, so there will be an impact, right? A hits B, and that's where the impact happens. So this is before impact. This is during impact, and this is after impact. Traveling, A goes faster than B, so A is going to hit B from the back. They both are traveling along the same straight line. Remember that. That's case one, direct central impact. And because of this impact, obviously A is going to apply a force to B, and B is going to apply a force to A, as we said, Newton's law. Newton's third law, these forces are the same. And then part of the energy of A, because of this impact, well, A had a higher velocity, obviously, because it could reach B and hit particle B or object B. So part of the energy of A is transferred to B. So they both continue traveling the same way, but most probably B is going now faster than was going before. And the velocity after is represented by VA prime and VB prime. Right? So they have some velocities before, some velocities after. In that case, right, we just use the general form of the equation we got here. MA prime plus MB prime plus MA is equal to MA VA plus MB VB, right? That we use MA VA prime plus, or you can just write it, maybe you have to write before first. MA doesn't really matter, it's just more of a MB VB, right? Vectors is equal to MA VA prime plus MB VB prime. Now, as I said, the question here is we want to find what are the velocities after. Now, in case one, outcome one, sorry, we had only one equation, this equation, and we're only looking for one velocity after the impact. Because those two objects or particles are attached to each other, there's only one velocity. They move with the same velocity. So this equation was enough, right? I could find V, the velocity after impact, by just knowing the velocities before impact and mass of the objects. Right? That would have been, this was enough. Now, in this case, because they get separated, I have VA and VB, or the velocity of object A and velocity of object B after the impact are not the same, right? It's not the same object. You have VA prime and VB prime. So now you have two unknowns here. How do we solve one equation, two unknowns, right? That's the that's something that that's where we are right now. We have one equation from what we had, conservation of linear impact for the conservation we derived from by using the principle of linear impulse and momentum, right, during the impact. Now we have this relationship between velocities before and after, but this equation has two unknowns. We don't know what is VA prime, we don't know what is VB prime, right? So this is one equation. Keep it there. Then what we're going to do is that we are going to use an extra equation that can help us, and that's the equation that relates velocities before and after using coefficient of restitution, right? So so this is one equation, two unknowns, right? And so as a result of this impact, right, part of the object's kinetic energy can be lost, right, due to a velocity of some different types of mechanisms that are involved in this whole impact situation. As I said, we're not going to go into details about those, but some permanent deformation. If you think two objects, when they hit each other, like in a car accident, obviously there are going to be some deformation in these objects, depending on how strong or stiff they are. You might have some generation of heat or sound, right? The accident you definitely can hear the sound of that. And that's part of the energy that is being released from the system because of the accident and impact. Now, to take into account that loss of energy, right, kinetic energy, right, we introduce something called the coefficient of restitution, which basically relates velocities before and velocities after the impact. And that's represented by E typically. So we put E is equal to VB prime minus VA prime divided by VA minus VB. Right? And I'll tell you a little bit about these negative signs. This is important. But so this is going to be the second equation. And remember, this is coming from the fact that as a result of impact, part of the object's kinetic energy, those objects are going to be lost. And we have to take that into account. Right? The total for the system, we have conservation of energy. But part of this energy is going to be converted into heat. Part of it might be converted into sound, might be converted into some permanent deformation, you know, in some objects, right? So the energy is lost. So not all the energy going from object 1 is going to go from object 1 to object 2, or object A to object B, or the other way around, depending on which one has higher energy. Right? There's an energy exchange there. Now this E, so let me put it here. This E, so now you have, before I get there, now you have two equations, right? First equation and second equation. These two equations actually now are enough for you to find two unknowns, velocities of objects after the impact. Now, this E, coefficient of restitution, let me call it, put here, it's called coefficient of restitution, right? This coefficient of restitution is, it really depends on properties of the objects that are involved in this impact, right? These objects, what are they made of? Obviously, when you have an object between two, when you have an impact between two objects made of steel, the deformation is different from when one of them is made of steel and the other one is made of aluminum, right? So this E depends on the objects, what material the object is made of, right? It depends on obviously velocities and the orientation of this accident, right? The velocities they have and the way they are impacting each other. So when they collide, and it's basically determined experimentally, right? It's not something that you can calculate. All right. So now you have two equations. E is determined experimentally, so you know that value. Typically for the objects that they're involved in this accident, as I said, they really run different types of experiments, different impacts with different angles, and they can give you some estimate for that E, depending on what materials are involved and what is the velocities and the orientations these objects have in the accident. So now you have two equations, two unknowns, so you can find velocities after the impact. And as a general note, I just want to add at the end that I told you when the objects stick together, that, as I mentioned here, that's the kind of impact because a perfectly plastic impact. Right? Now, this E is the parameter that you can use to figure out, or you can look at to figure out if it's a perfectly plastic or it's not. Right? Let's just put it this way. So E, this coefficient of restitution, can be any value between 0 and 1. In reality, it's never 0 or 1, but it reaches to these values. Now, in obviously, when it's very close to 0, very close to 1, we can always make that assumption that is 0. So if E is 0, one limit it can have, it's objects remain together. Right? So it's perfectly plastic. If E is 1, All right. Total kinetic energy is the same before and after the impact. So we have the perfectly elastic impact. So this would be perfectly perfectly elastic, right? Perfectly elastic impact, which means maybe I should have wrote the same way I wrote the other one. It tells us the total kinetic energy is the same before and after the impact. And that's when we have perfectly elastic impact, all right? So if it's perfectly elastic, all the energy from object A is going to transfer to object B, right? Total kinetic energy is the same. If it's E is not 1, then somewhere in between, part of the energy is going to be released. This kinetic energy is going to be converted to some other form of energy. You might have heat, sound, deformation in the object. If it's E is equal to 0, well, that's the case for outcome 1, when those two objects just stick together and stay together. Now, one thing I want to mention about the signs for these velocities when you're writing these equations, in coefficient of restitution here, pay attention, I put VB prime minus VA prime over VA minus VB. Now, this is for this case, right? If, as I said, direction matters. This is something very important that mistakes can happen, right? So this, let's take this as positive. If this is positive, VA is positive, moving to right is positive. So VA is positive before the impact, VB is positive before the impact. Right? Impact happens, VA prime and VB prime, they both are still positive. They're going to the right, both objects. If that's the case, this equation is valid. Now, what if that's not the case? What if object A is coming to the right, from the right, and object B is going to the left? Right, so VB would be negative. So when you plug in the values in this coefficient of restitution equation, instead of VA minus VB, you have to put VA minus VB. Right, this equation is for the case when VA, VB, VA prime, and VB prime are all positive or in the same direction, positive direction. Now, if any of these, the direction for any of these changes, right? It's negative direction, let's say, and remember, we're talking about direct central impact. They're all on the same, they're on the same straight line. The only thing that changes can be the direction in which they are moving. So if let's say A after the impact starts moving to the left, then VA prime would be negative, which means in this equation, in the numerator, you have to put VB prime minus VA prime, because VA is negative. So keep in mind, this relationship that I put here for the coefficient of restitution is for this case. Then everything is positive. All right. You can think about it this way: the velocity of object B after the impact minus velocity of object A after the impact over velocity of object A before the impact minus velocity of object B before the impact. Now, those velocities, positive or negative, you have to take that into account when you're putting it in this equation. All right. You'll see that in probably the first example I'm going to go over that. We'll see how we actually determine this positive and negative. You have to decide about the positive direction first. Again, momentum method. Impact is part of momentum methods. So the direction of velocity matters in the equations that we write. All right.